we're going to talk about kind of the idea behind why we use mass and moles to measure things, ultimately because atoms are very small and very light, and I don't know how else to count them. Remember how I was making a big deal out of like neutrons and protons and how much mass they have and mass number? Remember that? This is going to come up again. So as it turns out, the mass of a proton or a neutron is actually really small. It's like that. This is one mass unit. It's 1.66 times 10 to the negative 24. Thank you very much. So we're going to come up with a counting number so that we don't have to think about atomic mass units directly. And what we end up doing is we start using the mole number, which is over here. Great. Not that kind of mole. It's this is a mole. That's the mole number. There's more places to it. You can take it out to many places if you look it up. It's a counting number, like a dozen. So if someone says, hey, I have a dozen eggs, you're like, OK, that's 12 eggs. Well, if someone says, I have a mole of atoms, or a mole of molecules, or a mole of stars, they mean that many of those things. So I don't want this to seem that mysterious. This is called, Avogadro's number. And that many of an element will have the mass of its atomic mass. That's really useful. So if you look on the periodic table, you'll see that hydrogen has an atomic number of 1, and also usually there's an atomic mass listed, and it's listed as 1.008 or 1.0079 or something. And that number literally means that there's 1.008 grams per mole of hydrogen atoms. So if I had a mole of hydrogen atoms, it would have the mass of about 1 gram, or 1.008. And the different elements have different masses, right? So carbon has an average atomic mass of 12.01 or so. And that means that if I had 1 mole, if I had 6.022 times 10 to the 23 carbon atoms, they would have a mass of 12.01 grams. So this is tremendously useful. It allows you to count things, count moles or even numbers of atoms or numbers of molecules simply by knowing the mass. Chemistry has taken something that's really, really small, really, really hard to think about, impossible really to see with the naked eye, and made it accessible to you, just sort of like the problem-solving method. And you try to figure out what are they asking. And I swear, you're probably thinking of being condescending by covering this. I'm not trying to be condescending. This is the #1 reason why I get things wrong. I don't know if it's the #1 reason why you guys get things wrong, but it's because I misread the question. #1, so what are they asking for? Is it moles? Is it mass? Is it number of atoms? Is it something else? Figure out what information is given. So once I know those two things, then I have to figure out how do I get from the given stuff to the stuff I need to get for the answer. And then you kind of think about, well, if they gave me mass and molecular mass, is there a formula I know that will give me moles from that? And sometimes it gets more complicated than that. You'll have to calculate one thing to then use it in another equation. So you might have to use 2 different equations to get your answer. Or you might have to think about the chemical reaction and the balanced chemical equation to do it. But we'll work through some of these. You have to do the calculation, and that means sig figs, in addition to actually doing the calculation. And then a check is good. So coming up with some way to check is very, very useful. So let's see if I can pull these off without a calculator. You measure 1.73 moles of aluminum. What is the mass? OK, so we're looking for mass. So the units would be grams. Yeah. OK, so someone says C. OK, so that's what I like that one. So the way I'm doing this in my head, and it's pretty lame to be doing it in my head, is I'm like, OK, mass equals moles times molecular mass. The molecular mass is 26.98, or about 27, and we're multiplying it by about 2 or so. Almost double, yeah. So that's going to be bigger than 26.98 grams. This thing only, like for 1 mole, it's 26.98. For 2 moles, it would be like, what, 56 or something? So it's got to be this one. These are too small. Like, this is less than a mole. If I measured out less than a mole of this stuff, I'd get less than 26.98. So this is like the only good answer here. Sig figs look good. 3 sig figs, 3 sig figs. All right, you measure 45 grams of boron. How many atoms does this sample contain? Is 45 grams of boron more or less than 1 mole of boron? This is the mass for 1 mole of boron, right? Isn't this like 4 moles or so? Right, because like that times 4 is about that. Yeah, C's not, I mean, it's, so hang on. There's some interesting math stuff here we should talk about. So it's about 4 moles or so. I don't know what it is exactly. And it's also, the mole number is 6.022 times 10 to the 23rd, right? So that many grams of boron is a big number of boron atoms, right? Big number, huge, like multiple boron atoms, right? So this is a small number, right? Times 10 to the negative 25? Yeah, that's small. So I know it can't be C, and I can't be A either, right? Because how can I have less than 1 atom? I mean, it's not like fractional atom or something? I don't know. So I can't do that either. It has to be like many, many, many atoms. So B or D, and I know it's more than 1 mole, right? A mole is 6.022 times 10 to the 23. So this is less than a mole, so it's got to be B. Okay, so yeah, I mean, is that useful for me to beat up the bad answers? It's easier than calculating it, so I end up doing it. Because I don't want to bust out Excel, and I'm too lazy to make you guys tell me stuff. All right, what is the mass of 1 mole of sulfur dioxide? I will look up on the periodic table the molecular mass, the atomic mass of sulfur, and I'll add that to 2 times the atomic mass of oxygen. Because there's 1 sulfur in there, and there's 2 oxygens in there. And that'll give me the molecular mass. That's all you have to do. So yeah, there's 1 mole of S atoms, so I'm just going to multiply 1 times the molecular mass of sulfur, and I'm going to add oxygen, and then I'm going to add it a second time, because there's 2 oxygens in there. And that gives me the molecular mass of sulfur dioxide. And I should probably change these units because they don't make sense, especially when they have, they should be grams per mole. Yes?
The 16 and 32, the atomic numbers of sulfur and...
They are the atomic masses.
Okay.
Yes. So you might be getting confused because this is pretty close to a whole number, right?
Yeah.
I mean, yeah, some of them are close to whole numbers, but when you're looking at the periodic table, you'll see that there's the whole number that goes up by 1. That's the atomic number.
Okay.
And then the one that's fractional, sometimes it's pretty close to whole, or it is listed as whole. That's the molecular mass. Usually it's in the bottom.
Yeah.
So the smallest unit into which a pure substance such as sugar or water can be divided while still retaining its composition and chemical properties is and what? Okay, is it a mixture? Yeah, I mean, you can separate mixtures. We talked about that in class. Sometimes you distill stuff, filter stuff. It's not mixture, yeah. Isotope? I mean, that doesn't even make sense, right? Isotopes are elements that have different numbers of neutrons, and they kind of have the same chemistry. So they still have the same properties for the most part. So it's not isotope. Ion, not everything divides into ions. It still has the same properties. So
What
not
about
atom actually wouldn't be bad.
Unit.
Yeah, but the thing is, like, they gave us sugar and water as examples. Sugar and water are molecules, right? Like, water is H2O. If you burn it, or if you, like, I don't know, blast it with light or something until it breaks apart, the pieces don't have the same properties anymore.
So it's a
Yeah, and yes, that would be a chemical change, and you change the chemistry of it, so its chemical properties are at the molecular level. So if you change the bonding of something, then you've changed its chemical properties. So you can't really break up a molecule without changing its chemical properties. That's kind of subtle, because we did talk about atoms before. Compounds. Yes. So before, we had talked a little bit about empirical formula and molecular formula and how they're different. And these are not terribly great examples for that. But molecular formulas have to do with the smallest, like the number of atoms, elements that are in a unit, just one molecule. So H2O isn't like a euphemism for something or like a counting number. Literally, water is H2O. It has 2 hydrogens and an oxygen. That's water. That is what water is. This sugar, C6H6O6, this is glucose, for example. That is the smallest molecule, has 6 carbons in it, has 12 hydrogens in it, has 6 oxygens in it. That is what the molecule is. Like if I was to like make a model for it, it would have 6, 12, and 6 of those. The empirical formula for glucose is CH2O. It's just a ratio of the elements, the smallest ratio you can come up with without using fractions or decimals. So it really doesn't tell you anything about what the molecule looks like at all, except that you know that there's like a ratio of that many C's to that many H's to that many O's. But molecular formulas don't break it down further. They just say, okay, what does the molecule look like? That's how many of each element are in it. So we talked about molar mass. We talked about how to calculate it. So for methane, for another example, we have 1 carbon and 4 hydrogens in each methane molecule. So that means that when we calculate the molecular mass, we're going to add the atomic mass of carbon to 4 times the atomic mass of hydrogen. Okay, yeah. So we can start thinking about how much of a percentage the mass of something is, or like the mass of a particular element is inside of a compound. This is a better question, though. I like this. So the atomic mass of oxygen is about 16 grams per mole, and the atomic mass of hydrogen is about 1.008. So which of these looks right to you? Somebody says C. Anybody say anything but C? C looks good to me. So for oxygen, 16 grams per mole, and for hydrogen, 1.008 grams per mole. 2 of these is 32, and 2 of these is like 2. So 32 and 2 is 34. So good job. So you could actually think about what fraction of that 34 mass units, or that 34 grams, comes from hydrogen. That would be 2 times the atomic mass of hydrogen divided by the total mass of the compound. So that's how you calculate percent composition.